system. So the final equation was that it was mx double dot plus kx equals to 0, where m is the mass of the system, k is the stiffness, x is the displacement, x double dot is the acceleration, which was acting on the system when it was displaced an amount x. Okay, so finally from this equation, so we have simplified it to this one, x double dot plus omega n square x equals to 0, where omega n equals to, this is not w, this is omega n. Okay, omega n. So this is the frequency. Okay, omega is the frequency of the system and omega n is the natural frequency. So for a single degree freedom system, I told you that there will be only one natural frequency of the system. Okay, so this equation was derived by using what? Newton's second law of motion, isn't it? Where summation of external force will be equals to, so these are the external force, summation of external force will be equals to m into a, mass into acceleration. Okay, so these are the external forces which was added or which was acting on the system. One was the downward force, another was the spring force. Okay, where delta is what? Delta is static deflection of the spring. Delta is called as the static deflection of the spring, and x is the distance through which the spring is again displaced from the equilibrium position, isn't it? So our initial diagram was this one. Okay, so this was the unstressed condition when there was no mass. So the spring was spring length was the minimum length, then mass was added, then this is the static deflection. So where mg equals to k delta, spring force will be equals to the weight of the system. So then again it is displaced by the amount of x. So total spring force which will be acting on the spring, so its nature will be compressive in nature. Okay, spring force nature will be compressive in nature because you are applying tensile force to elongate the spring. So the spring will try to compress itself. Okay, and it will try to regain its original shape. That is why the spring force will be this one. Why this spring force is k into delta? Because we know that spring force F equals to what? K into x, isn't it? So if x amount of displacement is there, so spring force F will be equals to k into x. F equals to kx is the spring force. So kx, so in terms of x here I will be writing delta plus x. So this is the total displacement. Okay, so finally after using Newton's second law of motion, so we found out the motion to be mx double dot plus kx equals to 0. So this is what? This is a second order, okay, d square x by dt square, second order differential equation. And for every differential equation, a linear differential equation, so there is a solution, so which I think you have all of you have studied in mathematics. Okay, so how to solve this type of differential equation. Okay, so today we will going to see the solution also for this differential equation. Yeah, finally I told you that this is the you can express this final expression of motion as a simple harmonic motion. So here this is the acceleration which is directly proportional to displacement, and it is acting opposite to displacement because of this negative sign. Okay, now the same system, motion of the system can be solved, okay, not solved, can be derived by D'Alembert's principle also. So earlier we were using Newton's second law of motion. Now we can use D'Alembert's principle to find out the equation of motion. Okay, So what is D'Alembert's principle? So D'Alembert's principle, suppose when a system is not in static equilibrium condition, suppose it is in dynamic state. So what we can do in dynamic state means what? So there will be some motion on the system. So when there will be a motion on the system, so there will be one acceleration, isn't it? So that dynamic system, so we can assume that that dynamic system can be set to rest. Okay, the dynamic system can be set to rest. So when we will apply an external inertia force, which will be equals to mass into acceleration. Okay, so one dynamic system which will be having some motion, so it will be having some acceleration, isn't it? So the inertia force will be what? Mx double dot. So if mass is m, so what D'Alembert said actually, so that dynamic system can be taken to rest when you will apply one inertia force which is exactly equal to mass into acceleration in the opposite direction. Means by the application of that inertia force, you can set the body to be at rest. Okay, so actually what actually I want to say that this is the dynamic body. So the acceleration is in downward direction, it is happening. Okay, so this dynamic body, we will not consider any force. Okay, we will not consider any force. We will not consider this one. Okay, so we will only consider the spring force. We will consider only the spring force. Okay, on this system. So this dynamic body, so where there is a spring force which is acting, okay, in the upward direction, so that system can be set to rest when you will apply one inertia force which is exactly equal to mass into acceleration in the opposite direction. So here the direction of the acceleration when you are displacing in the downward direction is x double dot, and it is downward direction. So now this system, this is in dynamic state, so this system can be set to rest when you will apply one inertia force, okay, mx double dot, in the opposite direction to the acceleration. Means in the upward direction, so we will assume that there will be one mx double dot force. Okay, so now your equation will be mx double dot, because it is in upward direction, so you can write minus of mx double dot minus of k into x. Okay, because k delta and mg will be cancelled out, isn't it? Because k delta and mg is equal, or they are equal, so only minus of mx double dot minus of kx will be equals to 0. Means plus of mx double dot plus of kx will be equals to 0. Means finally we will get the same equation, that is mx double dot plus kx equals to 0. Okay, so the statement is written. It states that a body which is not in static equilibrium by virtue of some acceleration, so can be brought to static equilibrium by introducing on it the inertia force, which can be considered to be external force. Okay, so this inertia force, which is exactly equal to the mass into the acceleration of the body and acts through the center of gravity of the body in the direction opposite to that of acceleration. Okay, so this is our spring at the displaced condition. Okay, this is the mass at the displaced condition. So here the spring forces were k into delta plus x, and mg was there, so mg and k delta will be cancelled out, so kx will be acting upward. And if you just apply one inertia force in the opposite direction, which will be acting to the cg of the body. Okay, so though here I am drawing the forces, but here the inertia force will act through the cg. Okay, to show it distinctly, so we will be writing by the side. Okay, so through this also you can write the inertia force, which is assumed force mx double dot. Okay, so by the application of which you can set the body to at rest, or you can brought the body at rest. So two forces will be there, kx in the upward direction and mx double dot, which is taken by this D'Alembert's principle. Okay, so both these directions will be upward direction. So negative of mx double dot negative of kx, it will be equals to 0. So positive of kx plus positive of mx double dot will be equals to 0. And finally you will get the same equation which you got by Newton's second law of motion also. Okay, actually this D'Alembert's principle sometimes simplifies some of the problems. Okay, so when you will be using Newton's second law of motion, then the equation may be some lengthy equation. Okay, so in some time we will be using D'Alembert's principle to solve problems directly. Okay, so now this differential equation, second order differential equation, so we are going to solve this differential equation because we need the solution. Okay, so how to solve this differential equation or the equation of motion of the undamped free vibration of single degree freedom system? So the final equation was this one, mx double dot plus kx equals to 0. Okay, so you can rewrite this equation by using omega n square. So this is desired, actually this is needed. So x double dot plus omega n square into x equals to 0, where omega n is the natural frequency of the system. Okay, so here this equation is a second order differential equation, and the standard solution, this type of differential equation, if you remember in mathematics, okay, you have written the solution of this type of differential equation to be a combination of sine and cosine function. Okay, where there are two constants a and b. So the solution is given by the standard form x equals to a sine omega nt plus b cos omega nt. Okay, so I have written directly because by mathematics this type of differential equation can be solved by this standard form. Okay, so here we need to find out the value of a and b as well as the other things. Okay, so we need to find out. So this is the displacement equation x, because it is in terms of x, so we can differentiate this with respect to t. Okay, so then you will get the velocity. So if you just differentiate it with respect to t, so the velocity will be x dot equals to, so omega n will comes out, so for sine there will be cos, so a omega n cos omega n t. So for cos it will be sine, but negative sign will be there, so minus of b sine b omega n sine omega n t. So you just give it some number, this is 1, this is 2, this is 3. Okay, 2 and 3. Now to find out the constants, so these a and b, so we will be using some initial boundary conditions. Okay, so initial boundary conditions, so where we will be using the initial conditions? So on the system, okay, on the displaced system we will be using the conditions. So which is a displaced system? The spring mass system, which was taken initially. Okay, so this is the system. So let's say initial displacement means this is a free vibration, so you need to give some initial displacement. So initial displacement means what? So earlier the motion was 0, isn't it? So now you are giving some initial displacement. So initial displacement is taken as x naught. Let's say it is x naught. So at t equals to 0, because this is initial displacement. Initial word means what? It is t equals to 0. Means at t equals to 0, displacement was x naught. Okay, so x equals to x naught at t equals to 0, when time was equals to 0, initial displacement. Okay, so t, when time equals to 0, the in displacement x equals to x naught. So here it is written x equals to x naught at t equals to 0, and at that condition at t equals to 0 there was no velocity. Okay, so there was no velocity. So at this condition, so the velocity was 0 when the time was 0. Okay, so means the body was not coming from anywhere in dynamic condition. The body starts its motion from rest condition. That is why when time was 0, the velocity is also 0. Now what we will do? So we will put this condition separately. So this condition in equation 2, and the velocity condition in this velocity equation. Okay, so we will put what we will get. So x equals to x naught when t equals to 0. Okay, so in terms of x, so instead of x, so we will write x naught. So capital X naught you will be writing. Okay, so in the terms of instead of x, so I will be writing here x naught. T equals to 0 means what? Sine 0. Okay, so this term will vanish. So this will be 0 plus b cos omega n t. So t equals to 0 means what? Omega 0 cos 0 equals to 1. So means what? X naught equals to 0 plus b. Okay, means the value of b is capital X naught. Now this condition, when time equals to 0, initially the velocity was 0, so x dot equals to 0, so this condition we will put, so x naught will be equals to 0. Okay, so at t equals to 0, for cos function it will be 1, so a omega n will be there, minus b, so sine function will be 0, means what? It will be 0, sine 0 equals to 0, so b omega n into 0 will be equals to 0, means here only 0 equals to a omega n you will get. So omega n cannot be 0 because a system is having one natural frequency and it is having some definite value, okay, positive value. So omega n cannot be 0, so a should be 0. So from these two equation, so what we can write, so b equals to x naught and a equals to 0. Now the equation which was taken as the standard solution, this one, so here, so I will be putting the value of a and b, and the equation which will be formed will be the final solution for this equation of motion, okay, of an undamped free vibration of a single degree freedom system. So now I will put the value of a and b. So what? A equals to 0 means sine omega t term will vanish, so b equals to a omega n. Okay, so we have got b equals to b equals to x naught. Okay, b equals to x naught. So x naught we will put here, omega n will be there, sine omega n t. So here substituting these values of a and b back in the equation 2. Okay, so this is equation 2. So we will get x equals to, instead of b I will be writing x naught. Okay, so you can write here capital X naught. Okay, though it is written small x, but you should write capital X naught cos omega n t. Okay, so this is the basic equation of motion. So here, so this is the equation of motion. Okay, so I have told you that the simple harmonic motion will be a motion which can be represented by sinusoidal curve or cosine curve. Okay, so this is represented by a cosine curve, cos curve. Okay, so if the motion was started from the upward direction, then you will get one sinusoidal curve. Okay, as because you have started the motion from the downward position, okay, means you are displacing it in the downward direction, that is why you are getting the curve as cosine curve. Okay, so this is the actually proof why the equation of a simple harmonic motion is cosine curve or a sinusoidal curve. Okay, so this is the equation of motion, and this is the solution for that equation of motion of a single degree undamped single degree freedom system. Okay, where small t is not a time period. Okay, it is instantaneous time anywhere on the path, it is the instantaneous time, but capital T, so in terms of omega n you can write 2 pi by capital T. Okay, because that will be your natural frequency. Okay, so omega n, so t equals to 2 pi by omega n, this is the time period. So if you are asked to find out what is the time period, then you need to write t equals to 2 pi by omega n, then you will be able to get the time period for that particular equation of motion or that simple harmonic motion. Okay, so this is all about the analysis, okay, for an undamped free vibration of a single degree freedom system. Okay, so what were the assumption? So mass was rigid. Okay, it was not showing any elastic property, that the mass, okay, particularly the mass, the system is elastic because there is a spring, okay, or stiffness which is having some stiffness k, okay, small k. Then spring is massless, the spring is massless, and the main thing was that the sign convention, okay, means when we are taking any parameter in the downward direction, so those things were taken as positive, and anything which is happening in the upside direction, whether it is displacement, acceleration, velocity or force, so those were taken as negative. Okay, so that way we have solved the equation or find out the equation by using Newton's second law of motion or D'Alembert's principle. Okay, so if you have any doubt, you can ask. Okay, let's move. In this particular system, there was only one spring, isn't it? Suppose there are two springs, okay, which are connected in series or in parallel. Then how to find out the natural frequency of the system, or how to find out the equivalent stiffness of the system? Because it is very much important to find out the stiffness of the total system. Okay, then only you will be able to find out the natural frequency. Okay, so here time period is found out by 2 pi by omega n, and if you are asked to find out if the time period is given if you are asked to find out the natural frequency, if the time period is given, then you will be using the same formula. Omega n will be equals to 2 pi by time period. Okay, now let's see this thing. Okay, so here you can see two springs are added. Okay, there is one node, you can see there is one joint. Okay, here in a small circle it is shown. So this is the node, so two springs are added, so K1 and K2, which the stiffnesses are K1 and K2. Okay, what is the unit of stiffness? If I asked you, it will be Newton per meter, because spring force is what? F equals to Kx. So K will be what? F by x. So F equals to Newton and X equals to meter in SI unit. So Newton per meter. Okay. So here, how you will find out the equivalent stiffness, because we need the equivalent stiffness. Okay, to find out the frequency. Okay. So how you will find out? So you can see the weight. Okay, the concept is that the weight of the system. Okay, the weight of the system is shared by this spring K1 and this spring K2. Okay, or you can say the spring force. Okay, the force. Yeah, one more thing. So see the deflection. What is the deflection for this spring? There will be delta 1. For this spring, there will be deflection delta 2. So the total deflection of the spring, when you add this mass, so that will be how much? So let's say that is delta or delta st. So that delta will be equal to delta 1 plus delta 2, isn't it? So the total displacement of the mass will be the summation of the displacement of this spring delta 1, okay, which is having stiffness K1, and for this spring it will be delta 2, means delta 1 plus delta 2 will be equals to delta or delta st. So this is the concept to find out the equivalent stiffness. So what is delta 1? So delta 1 will be equals to mg by K1. I have told you the weight is shared. Okay, the weight is shared by the forces or by the springs. Okay, so the deflection is also shared by these two springs. Okay, the total deflection is delta, so individual deflection will be delta 1 and delta 2. So delta will be delta 1 plus delta 2. So what is delta 1? So delta 1 is deflection, the spring force divided by the stiffness. Okay, the spring force will be equals to what? Mg. I have told you, because the static deflection will be equals to the weight of the system. Okay, so on both the springs they will feel the same weight, which is acting downward. Okay, mg. So mg by K1 means spring force by the stiffness, so that will give you the delta 1, though here it is mg, but it is the spring force. Okay, instead of K delta, I am writing here mg, because it will be balanced in static equilibrium condition. So mg by K1 and delta 2 will be mg by K2. So mg will be equal, as I have told you, that the spring force or the weight which the two springs will be felt will be equal. So mg by K1 plus mg by K2. Okay, so here it is written. So mg will be equal, isn't it? So total deflection will be what? So mg by K equivalent, total deflection, so which will be equals to the individual deflection. So from this, so you can write 1 upon K equivalent will be equals to 1 by K1 plus 1 upon K2. Okay, So this is the equivalent stiffness. Okay, if you are asked to find out what will be the equivalent stiffness in this type of connection, so it is by this expression. Okay, so you need to remember this expression, and this type of connection is called as series connection. Okay, so end-to-end connection or series connection, because the total spring force it will be total displacement, it will be shared by the individual displacement of the two springs. Okay, and here delta 1 will not be equal to delta 2. Okay, because the stiffnesses are different. Okay, now springs in parallel. So when you can see, this is the system parallel connection. Okay, so here you can see the total delta is equal to, when the two springs are connected which are having stiffness K1 and K2, so the total deflection of the mass will be equals to the individual displacement, okay, of the two springs. Means delta will be equals to delta 1 equals to delta 2, means whatever be the displacement individually by these two springs will be equal to the total displacement, isn't it? So by how much amount of amount it will go downward, that same amount will be for K1 spring, and same amount will be for K2 spring. Means delta 1 will be equals to delta equals to delta 1 equals to delta 2. So directly you can write K equivalent will be equals to K1 plus K2. Okay, or instead of this you can write that spring force F1 plus F2 will be equals to what? F equivalent. So by this force equation you can write, so F1 is the spring force for K1, F2 is the spring force for K2. So these two spring force will be equal to the equivalent spring force. Okay, F equivalent. So you can write F1 will be equals to K1x, F2 will be equals to K2x, because xx will be equal for these two springs, as because they are parallel. Okay, so K equivalent x, so the total this deflection will also equal. Okay, so from this equation you can write K1 plus K2 equals to K equivalent. Okay, so the same concept is used here also, but I suggest you to use this concept. Okay, so this one will be easier for you, as because here also you use the same concept. Okay, so delta equals to delta 1 plus delta 2, here delta equals to delta 1 equals to delta 2. Okay, so I think now you will be able to solve problems where the few springs will be there, okay, in a system. So what you need to do actually, so you need to find out the equivalent stiffness. Okay, why equivalent stiffnesses are actually found out in any problem? Because you can see what was omega n basically. So when we use the equation mx double dot plus kx equals to 0, so omega n square equals to k by m, means omega n will be equals to what? Under root k by m, isn't it? Under root k by m, means omega n depends on stiffness and mass of the system. So if one spring is there, so directly you can write k, but if 2-3 springs are there, so you need to find out the equivalent stiffness to find out the natural frequency of the system. Okay, you can see one problem. Okay, we will cover this topic in the next class. Okay, so this is simple problem, so where you are asked to find out actually the natural frequency. Okay, so the natural frequency, I have told you that it is found out by using finding out the value of the mass of the system and the stiffness of the system. So here you need to find out the mass component and the stiffness. Okay, and and you need to find out what the equation of motion also for this particular system. Okay, okay, this one we will cover in the next class. Okay, so till now if you have any problem, then you can ask. Does anyone wants to ask anything? Okay, thank you, students. for joining. I will be uploading this video tomorrow. Okay, tomorrow in the college. Okay, then you can leave this meeting. Thank you.